This is the third part of the Corl 23 discussion. Today I want to focus on Dieter Fox in particular, also add some of Sergey Levine's comments. I already spoke about Sergey Levine in the first part, which I think is the biggest takeaway for me for robotics in general, his idea that we should think ahead in terms of having a large fleet of robots and then focusing on how we can take advantage of that in terms of data pipeline and modeling and those sort of things. So what I want to talk about today is a little bit more Sergey Levine, particularly offline reinforcement learning, but I think the key is really Dieter Fox. I think Dieter Fox, he's at UW and NVIDIA. In my opinion, he's a thought leader, not just a researcher, and he's focusing on sim. And I think I have said that many times before, simulation, in my opinion, is the path forward. And we can use different approaches. We can use sort of the AlphaGo Zero approach, where you do everything in self-play. That is relatively difficult with robotics, but I think Fox's approach, which is an iterative approach. So we generate data in sim, train it, then go back to real, take the learnings, go back to sim, and so on and so forth. I'm going to talk about this in more detail, but that's the key. So we have a foundation model that is bootstrapped in sim and then goes to reality and then back and forth. This is not even on podcast. It's November 28, 2023. This is Delco for the day. Fund is up 8.7%. The market is up 10 basis points. For the year, we are up 115.1%. The market is up 18.7%. We're outperforming by 96.4%. So the third part is of Corl. Let me start with Dieter Fox. So Dieter Fox presents a paper and also in a talk at MIT a couple of months before. And I presume he also gave a talk at Corl 23. I couldn't find it because I wasn't present physically. That's why I'm not able to find it. But that's okay. I don't think his opinion must have changed much since the MIT talk. So I'm going to focus on that and relate it to Corl 23. I hope this confusion is okay with listeners. So anyway, so what is he suggesting? He's suggesting a foundation model for robotics. And in a nutshell, what he's suggesting here is that we create a foundation model in simulation and train the robot in sim, then use that learning, turn it into real, test it in real, take some of that data back to sim, enhance the model. So what that means in practice would be, for example, you have a couple of things that you can fine-tune in sim and then post. You can fine-tune, let's say, the policy. You can fine-tune task definition, and then you can see how it works in reality. For example, is it enough to teach the robot to open, to have a task which says open, and then within the context of, let's say, open a drawer versus open a cabinet versus open the car door? Is that enough, or do you need to be more specific? Those are questions that we're not sure yet how a robot can, from an engineering perspective, actually execute those tasks. We don't even know whether we should be more specific or less specific, and how can we generalize. But I think the fundamental idea of a foundation model really is exciting. Okay, why not take the learnings from the large language models and translate them into robotics? And we could do that with foundation models. And because we have a problem with robotics in general, they're expensive, they're difficult to build. How about we go in sim? Now, of course, some people might say, well, this is just NVIDIA talking their book because Dieter Fox works for NVIDIA. But sim has a lot more legs. This is not just, trying to sell NVIDIA technology to the world. This is really interesting. So Fox's hypothesis is the following. Can we generate vast amounts of robot manipulation data, build foundation models on top of that data, and then train generalizable robots? If you can get enough data, transformers can actually shine. Now, what are the tasks we need to teach a robot? Let's say a sort of a humanoid robot. Let's be, okay, let's put a couple of definitions out there. Embodied intelligence is a robot, okay? So embodied intelligence equals robot. And it could be a car, it could be a humanoid robot, it could be something in physics that executes a task. Let's leave it at that. Now, we have the full self-driving suite and the whole situation with Tesla, of course, and that is a little bit different than an embodied robot that is moving around in a factory. That's also why Tesla has a humanoid robot business and they have a full self-drive business. They separate those businesses. Maybe eventually it will just be one, but today we're still separating those two. And the fundamental difference is that the way a car moves around in traffic is a lot more controlled and it's a lot different than the way a robot moves around on the factory floor. And then there's one particular skill that a car doesn't have to execute, which is grasping. And that is what a lot of robotics people are focused on, at least sort of the embodied slash, when we talk about robotics, that's what we imagine, okay? We imagine this thing going around in the kitchen, cleaning after you, bringing you tea, making coffee, making scrambled eggs. That's what we imagine. Now, that, of course, doesn't have to be a robot necessarily. A robot can be anything, but let's just leave it at that for now so we don't get entangled with definitions, right? So the robot that I'm talking about is embodied intelligence, but it's not a car. It is this thing that, goes around in the kitchen and does stuff. Now, that thing needs to do a couple of things, and Fox is kind of looking at it from a task-specific perspective. He talks about it like, number one, he needs to recognize. Okay, the thing needs to recognize. Then he needs to be able to pick up, right? And then he needs to do some sort of task, recognizing, computer vision, pick up. That's actually a pretty difficult problem. And then we have clipboard, which is what UDOP created, which is a text-based task manipulation sort of engine, right? So what we have is, I tell the robot what to do. Go and make me scrambled eggs. Now that LLMs can deal with that because they're very good at task distribution. They're very good at telling something what to do. We've already seen that in even Microsoft, Andrej Karpathy spoke about this, that LLMs could be a new operating system for X. They could be an operating system for for a computer. It could be an operating system for getting tasks done on the internet. But they can also be an operating system for a robot, right? Go get this done. So what does it mean to be an operating system? It just means that you delegate tasks. It's kind of like a task delegator. Walk over there and pick up an egg and go make me scrambled eggs. That's what an operating system does. It then translates this task into lower level actions. Walk over there, grasp, make eggs, etc., etc. The recognition part, that's computer vision. We have stable diffusion. We have nerves. We have a couple of ideas on computer vision of how to deal with the recognition part. We also have the depth, which could be solved through nerves, for example. So there's a couple of approaches that are sort of parallel here. I mentioned Shuren Song's idea of using stable diffusion as a motion planning technique. So there's a couple of overlapping ideas. But what I found most interesting about Dieter Fox's approach is this idea of building a foundation model. So literally tokenizing the space. You can use URDF, for example, Unified Robot Description Format, right? You can use that, for example. Now, I don't want to get too technical about this, but you could use some sort of format which says this is the scene, this is where things are, and then in each epoch, so every time step, let's say 50 milliseconds, or each time you make a move, you redefine the situation. Well, you're still, you're a meter away, now you're meter minus x away, meter minus 2x, meter minus 3x, meter minus 4x, and whenever you generate this new RDF, you have a different scene, and then at some point you are in front of something. Well, don't hit this, go somewhere there. You learn that, of course, through a neural net, so you don't need to hard code anything. That kind of idea is being propagated. Now, the fundamental idea of Dieter Fox, I want to make sure I don't lose track here. It is to start with sim, right? It is to not get boggled down now with the reality of physics and all that stuff. Start with simulation. Try to get a good enough approximation of what a robot should do, and then go in real, test it in real, collect data there, learn from there, and then you maybe enhance the simulation, do this back and forth. To me, this is the biggest takeaway of Dieter Fox's presentation at Corl 2023. To summarize, generate data in simulation, train foundation models, test it in real, go back to simulation, refine it, the foundation models, so fine-tune them with real, and hopefully at some point we get to a point where we have a generalizable robot. It's a path, it's an idea, it's not a closed-end solution or anything like that. In my opinion, it's the right way to think about it. And just to finish this part 3, I want to add a few comments about Sergey Levine. He gave an opinion piece where he spoke about the idea of having, of assuming that robots will get to a point where large fleets are deployed, and think about the deployment and all the necessities that come with it from that perspective. I think that's a good idea. Now, he also in particular talks about offline reinforcement learning, and I think that's one of those phrases that get thrown around. But what offline reinforcement learning really is kind of supervised learning, okay? And all of these things, in the end, foundation models, large language models, whether it's GPT or Llama or BERT, they're supervised models, because what you're doing is you're taking some sort of ground truth from human generated data, and then you're training the tokens to understand the relationships between the tokens based on the real generated data on the ground truth. And this same idea applies to offline reinforcement learning. It can be used as a bootstrap. I think this is the key idea. So I think to summarize, the difference between Levine and Fox is Fox wants to start with sim, Levine wants to start with offline. It's slightly different, but the idea is the same. Let's start in sort of virtual space and bootstrap the robots. This is the key idea. How can we bootstrap? So I think these two ideas are fundamental, and this is what I'm going to take to NeurIPS this year, is how can we bootstrap robots? Either we do it in sim or we do it through offline reinforcement learning. Thank you.